Alrighty, everybody. Good afternoon, and welcome back to your favorite class, also known as my guest bedroom. Okay. So, a couple of announcements. Quick. I think most of you got the email. You should have all gotten the email from Dr. Baumgartner about MSOE moving from normal grading to pass-fail grading this quarter for a variety of reasons. He sort of laid out a number of reasons in the email. I think this is, maybe a good thing, maybe a bad thing. Good in the regards that people that might get sick or people that have poor access to internet services or whatever, there's some compensation and some leeway there. But I think it can also be sort of a bad thing in the fact that it now gives you a little bit of leeway to sort of slack off in your classes and still pass. So generally, I'm not a huge fan of what they're doing, but hopefully you guys can still maintain your fire, maintain your passion, and come to class and really understand the material and get to work here with me. So I'm going to stick to the plan I've got going. I'm still going to grade all your stuff on a numerical scale. I'm still going to post everything to Blackboard. You're still going to have a numeric score on Blackboard. The only difference is now that you only need a C for my class to get a general passing grade. Okay. If you have some questions about what's going on there with that, you may consider just sort of reading over that email again. And if you do have some more deep questions, I think either talking to the department head is probably the best way to go, or seeking out some of the services that he describes in that particular email. Okay, so that's kind of the best thing I can really prescribe for what's happening, and I thought I'd just sort of bring that to everybody's attention so we all sort of know what's going on and are kind of on the same page. Okay, if I got a P, do you know about GPA? All right, Brian asked the question. So if you pass the class, it basically results in a no grade on your GPA. So there is a description about what happens to your GPA in that email, and that more or less is regardless of if you get a pass or no pass, it basically has no effect on your GPA. So, yeah, another question I have here from Ryan, will C still be a 70% for us? Yes, a 70% is a C. Actually, 69.9 and above is a C. So as long as you get a 69.9 in this class, then you pass, or you will see a passing grade on your transcript. C, D, and D is a low pass, which for all intents and purposes is still a pass. So you'll still pass the class, you'll still get credit for the class. It'll just show up as an LP instead of a P on your transcript. And if you get a 59.9 or less, then you'll get an F for the class. Okay, but based on what I've seen from all of you guys so far, you're crushing it so far. The homework's been great. Most of you are attending lecture, so I appreciate the effort that you guys have put in. I know it's a strange situation. Just please do your best trying to stay up with us. All right. So with an LP, you can continue on the ME track. Jorge asks, yes. So an LP counts as a pass, and you will be given credit for the class to continue on with the course. Okay. Those of you taking a class for grade replacement, which may be applying to some of you, some special circumstances. So I don't have all the questions for that particular answer. I would say if you have questions about grade replacement, I am not the right person to ask. Okay, so that's all I'll say about that. Okay, so globally, that's what's happening. Maybe many of you got the email and sort of had questions. That's the best I can do. If you have additional questions, seek some of the other resources that he's describing in that email. That's all I can really do for you. Okay. Next thing, your homework 2 still will be due at the beginning of lecture on Thursday, and your first exam for the class will still take place this Friday. I plan probably sometime tomorrow to send you guys an email with a lot of the specifics on how the exam is going to work. So there's not a lot really that I need to describe, except the idea that once 2 o'clock rolls around, I will release to you the exam. You will execute that exam on scratch paper in front of you. Then when you're done, you'll take a picture of it and submit it to me by email, just like you would submit a homework. And that's it. My exams that I'm writing for this particular term are shorter than I would normally have made them. And that's to sort of accommodate some extra time that you might need for scanning the homeworks, or not scanning, but scanning the exam or taking a picture of the exam or whatever method you've sort of been using so far to submit your work to me. Okay, so that's generally what's going to happen. I'll put that down in writing and send it out in an email probably sometime early tomorrow. Okay. We have Microsoft Teams open during the exam. Yeah, you'll have Teams open during the exam. I'm going to ask you all to turn your cameras on and point your cameras towards the work that you're doing. That's all I can really do. If for some reason that's difficult for you, let me know and we'll work it out. Please wait until I send the email tomorrow to sort of ask more additional complicating questions if that should be a problem for you guys. Okay. All right. So that's that. We're going to do an exam review, but I actually wanted to do it during the lecture period. I was considering doing an exam review sort of in later hours, which is something I normally do for classes like this, but I think we have enough time actually during the lecture period on Thursday to just go over some of the review questions or the practice problems that I handed out a couple of days ago. I think last Friday it was that I sort of handed those out. So just a reminder, your homework will be due at the beginning of the lecture on Thursday. You have practice exam 1 problems, which have been posted on Blackboard, so you can kind of look over those and review those. And we'll do some of those in class on Thursday, and that'll sort of be our exam review. Okay? So that's that. The agenda for today is going to be to finish up discussion on relative acceleration equations and do an example problem there. So Riley's got a question about homework 2. Riley, send me an email or come to office hours for that question. Do we get any notes on the exam or just an equation sheet? You have open everything for the exam, okay? You want to browse the internet? Fine. You want to have books in front of you? Fine. You only need 2 equations, okay? The relative velocity equation, the relative acceleration equation. That's it. You can have a zillion books in front of you. It's going to be a waste of time. I mean, if you know how to use the relative velocity equation, you know how to use the relative acceleration equation. That's all you need. So open everything, whatever you want. Okay. I can't police you. I'm not going to try. I just got to make sure that you're actually doing your own work and somebody else isn't sitting there doing it for you. So that's why I'm asking you to point the camera at yourself and at your work during this process. Okay. I will not give the answers for the exam. Come on, Aaron. Okay, so if that's all questions, let's get back into the material. So I'm going to transfer you guys over to my whiteboard here. Okay, so you guys should all have the whiteboard in front of you now. You know, my dog's over here getting kind of restless. Maybe I'll show him on camera a little bit later for a break. He's kind of bugging me right now. Okay, so you should all see the whiteboard in front of you, and I'll remind you kind of where we were last time. So last time, we introduced the relative acceleration equation. For rigid body motion. And namely is that if we had 2 points on a body, namely points A and B, the relative accelerations given by the acceleration of B is the acceleration of A plus the acceleration of B relative to A. Okay, and this is very similar to what we saw with the velocity equations, and namely that we have here this translational component. So the acceleration of B is going to be a combination of both the translational acceleration of A and what would be the fixed axis rotational component, or the acceleration of B relative to A. So this comes from basically like fixed axis rotation. Right. So we actually went through a couple of weeks ago now, and we derived the acceleration for fixed axis rotation. And so with fixed axis rotation acceleration, we come upon what is the general relative acceleration equation that we use over and over in this class, and that is that the acceleration of B is the acceleration of A plus the fixed axis rotation, which generally we say is the angular acceleration of body AB crossed with the position vector locating B from A, plus the angular velocity of the body AB crossed with the angular velocity of the body AB crossed with the position vector locating B from A. Okay, if you've kind of worked on homework 2, this should be very familiar to you at this point, since you've had to generally use this equation quite a bit. So as I mentioned before, this was box-worthy and sparkle-worthy, whatever you want to say, that this is one of the 2 equations that you use in this class over and over and over and over. Okay, so even after we get done with this portion of the class, when we start to move on to kinetics, which relates things like forces to acceleration, you'll still be using this equation over and over and over and over. Okay, so this guy, you know, he gets sparkles, he's very fancy. Yada, 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 sparkly, sparkly. All right. Sparkles are good. Again, translation. And then this entire back end is the fixed axis rotation, but we can further split up the fixed axis rotation into what we say is a tangential acceleration component. And this we say is a centripetal acceleration or centrifugal acceleration. All right, so this is sort of the acceleration component that points back inwards to the point of rotation. All right, so we introduced this equation. I want to dive in a little bit more depth on this guy, and then we'll do an example problem. All right, so I'm actually going to steal the image from your notes. So if you have the PowerPoints in front of you, I'm going to steal a particular image from that and sort of talk through what's going on in that particular image. So instead of trying to actually draw it for myself, which would probably be a disaster, I'm going to pull it up here, maybe explode it a little bit, make it nice and large so people can sort of see what's happening in this particular picture. Okay, so this picture is sort of a representation of physically what you might see from the mathematical equation that we sort of derived. Okay, so here, if we think about this point A down here as being pinned to this bar on a slider, and let's say we know generally what the acceleration of this point is. Let's say we know the acceleration of A, which I've kind of highlighted down here. Maybe I'll use blue since there's some red already in this picture. Okay, so let's say that we know that information and we're interested in what is generally the acceleration of B. That's kind of what we sort of want to know. Well, our equation would tell us up here that it is some combination of the translation of A plus what would be the fixed axis rotation of B relative to A. Okay, so the fixed axis rotation has these 2 different components to it, this translational and, or sorry, the tangential and the centripetal portions to them, and I sort of want to expand on that a little bit more. Okay, so this image is sort of trying to show that, and that the total acceleration of B here is the translational component. Here we see that the translational acceleration of B is the same as the translational acceleration of A. Okay, plus here these additional components on this other piece. Where here these components are from fixed axis rotation. All right. And we see sort of the 2 different terms that pop in from the fixed axis rotation. All right. So we have here, this is the tangential term. You see these 2 arrows here are sort of meant to denote it could be either one way or the other. So in reality, only one of these directions would be present, but you know, they're kind of showing that it could be occurring in either direction. And then here, this is the centripetal portion. All right, so here is the centripetal portion, and this guy up here is the tangential portion. All right, let's dive in a little bit more on this mathematically. Generally, this guy as a tangential portion is sometimes written, and you can see it here, but I'll make it a little bit more clear. This is the acceleration of B relative to A, and sometimes it's given this sort of T subscript, all right, for sort of the tangential component. And then this arrow here, you can probably see it on the image here. This is the acceleration of B relative to A, this fixed axis component. And this is a sub n for the normal component of that acceleration. Normal typically meaning pointing inward or outward away from yourself. All right. So we can sort of show what these might be mathematically. Recall that here we have that if we look at each one of these individually, sort of the tangential acceleration is this acceleration of B relative to A sub t. And this portion of the acceleration is the angular acceleration of the piece crossed with the position vector locating B from A. So that is this alpha AB crossed with the position vector locating B from A. Okay? Now we know from what would be the right-hand rule that typically this guy is in K hat, and this guy is in I hat and J hat, and that is for 2D. All right, so when we're talking in this class, our angular acceleration almost exclusively out of plane, the vector is defined usually in K, and our position vector locating B from A is in the plane, so with components I and J. And so when we have this cross product, we know the result will be perpendicular to the vectors that define each one of these things. And so we can see that if we move back up here to this particular picture. When we look at the vector here, I'll try to highlight it again, that sort of defines the tangential acceleration component. It is perpendicular to both the angular acceleration vector, which is out of the plane, and the position vector that locates A from B, which generally is this vector. Okay, so the perpendicular nature that I'm sort of talking about is this perpendicular nature here. Okay, and so we see the tangential component being perpendicular to the vector that defines B from A. Okay, and that's just generally sort of always going to be the case when we have this planar motion. All right. So that is sort of analogous to the velocity when we have like omega cross r, where we know that the velocity will be tangent to or perpendicular to the position of the piece in the plane. All right. So the tangential portion is there. And let's page down a little bit here and let's talk about the centripetal component. Or sometimes called the normal component. And this is A, the acceleration of B relative to A in the normal direction. And here is that second component of the fixed axis rotation acceleration. And that is omega AB, the angular velocity, crossed with the angular velocity AB, crossed with the position vector locating B from A. All right. Now, this one, when we simplify to 2D, is a little more complicated. But the idea here is that usually this guy is in K hat, usually this guy is in K hat, and usually this guy has some component, which might be like Rx I hat plus Ry J hat. Yes? Okay, so interestingly, when you have omega cross R, and omega is in K and R is in I and J, what happens is that this angular acceleration term will simplify to have a negative sign for the signs that are contained in the position vector. So what ends up happening is you will end up with a vector that looks something like the magnitude of omega AB squared, since we have two of them, multiplied by the negative of the position vector R B with respect to A. Okay, so this is sometimes written as negative omega squared r b with respect to a. Okay, and this is only for 2D. So that's a simplification for the 2D case. All right, so we more or less see that the normal component of the acceleration will be along the same direction as RBA, but will generally be pointed in the negative direction with a varied magnitude. Okay, so you see that again in this image. All right. So here's the position vector that locates B from A. It is here. And you will notice that the normal component of the acceleration, which is here, the acceleration of B relative to A, is pointing in the negative direction of the position vector that defines B from A. And that's because of this sort of double cross product that you have to go through, which is like omega cross R. All right, so what ends up happening is you do, here's your R, and you do an omega cross, it's going to point you right back to where you started. All right, so that's what generally happens in these 2D problems. All right, so we've done kind of a dive here on this. So if you like the idea of using this sort of shortcut, and for the tangential acceleration, kind of pretty simply here, if you want to cut this down by just writing something like alpha r bar, that's fine. But after this discussion, I just want to make one last note about sort of general relative velocity and acceleration equations. Okay, so we've had some discussion about some shortcuts that you might use for velocity. Remember, we talked about right-hand rule and the magnitudes of the velocity being the magnitude of r multiplied by the magnitude of omega. Okay, we've had some discussion about shortcuts for calculating relative velocities and accelerations. Okay, if you like some of these shortcuts, like calculating the velocity using these magnitude tricks and the right-hand rule, if that works for you, great. Fantastic. Make sure you know when that is useful and when it's not. If you like some of the shortcuts that I kind of just breezed over here for calculating accelerations quickly, which here might be something like using this shortcut to calculate the normal component of the acceleration. If you like maybe leveraging that or using that, okay, perfectly fine. Go ahead, I don't mind that. But I will say that there are some situations when this is applicable and some situations where it's not. Namely, in this class, we have 2D situations that we're almost exclusively looking at, right? Planar rigid body motion, which is kind of what this whole class is about. And so these shortcuts that I've sort of talked about all kind of rely on the fact that your angular velocity omega is always going to be k hat, and your angular acceleration is always also going to be out of the plane in k hat. And so some of these shortcuts sort of like require you to utilize or have those particular situations. All right. So far, we've talked about some of these shortcuts for calculating velocities and accelerations. And so if you want to use fine by me. Okay. I understand the methods, obviously. So okay by me. If you want to use them, you know when they apply. Fantastic. Otherwise, these equations always work.
And these are the two that you should absolutely commit to memory if you haven't done so already. First is the relative velocity equation, and that is the velocity of B is equal to the velocity of A plus the angular velocity of the object crossed with the position vector locating that object in space, RBA. All right, that's your relative velocity equation. And your relative acceleration equation is that the acceleration of B is equal to the acceleration of A plus the angular acceleration of body AB crossed with the position vector locating B from A plus the angular velocity of that object AB crossed with the angular velocity of that object AB crossed with the position vector locating B from A. All right. These two equations hold always. 2D, 3D, whatever, doesn't matter. Okay? Any situation that exists in our known universe. Okay? These guys will work. Okay? So no sort of assumptions required. It works regardless of condition. They always work. All right, assuming that you define all of these things correctly. Okay, so if you know how to use those equations, which hopefully I've been hammering on them long enough where you're starting to like get comfortable with them, you've seen them a lot in your homeworks at this point. I generally advocate for this strategy. Okay, you want to use shortcuts? I got no problem. But generally, I advocate for committing these two guys to memory, and those are the only two things you're ever going to need on, exams where I ask you questions about these problems. No trying to memorize tangential component, normal component. When can I use it? When can I not? Rah, 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 rah. Okay, memorize those guys. Put them in your head. They always work. All right. So that's that. I'll give you one last second here to sort of copy things down, and then we'll do sort of the last example problem from this deck, and that'll be all of the material that I'll ask you to remember for exam number 1. So this will be full coverage through the material for exam number 1, sort of up to this point. All right, how are we doing in chat? Got any questions? Microphone still working? Everybody still awake? Questionable. All right, thumbs up. At least Katie's awake. Okay, so I'm going to pop over to slides then and pull up an example problem. And this actual example will be a continuation of the crank problem that we did when we first introduced the relative velocity equations. Okay, so let's go ahead and we'll switch over to that. Okay, so we're back to this crank example, and we have the same constant angular velocity of the driving crank AB, and now we're asked for the acceleration of point B, the angular acceleration of rod BD, and the acceleration of the piston at P, which is sort of the same thing as the acceleration of point D. All right, so I'll leave this up for a second, let you guys sort of copy it down. I will also transfer it over to my writing pad over here, and then we'll work through that example. I forgot my elevator music for my lobby again today. Sorry about that. Wanted to get the elevator music going. All right. Okay, I'm going to switch over to the whiteboard here. I basically recopied down information from this slide onto the whiteboard, so we should all be able to keep going if you're still kind of copying the problem. And I'm kind of reminding you here about some of the other intermediate values for this problem that we actually solved for when we went through this example last time, doing the velocity analysis. So remember last time we did velocity analysis to determine that the angular velocity of link BD was 61.9 k hat radians per second. This is a piece of information we'll need later. And then also this angle beta that is formed between rod BD and the horizontal was 14 degrees. Okay, so those are two pieces of information we're going to need as we go through the acceleration analysis. Okay, so let's go ahead and make it rain. Let's make this thing happen. All right, so we already did the velocity analysis. Okay, and that's more or less where we got this information from. Okay, that was from the velocity analysis. My general theory is that if you're going to attack problems like this, you want to start with velocity analysis of the entire system and then do acceleration analysis of the entire system. So when you come upon homework problem number 3, for instance, which looks very similar to this particular problem, I would advise the full velocity analysis first to get things like angular velocities and velocities of points of interest, and then proceed with the acceleration analysis where you're analyzing for, let's say, acceleration of various points and angular accelerations of the various rigid bodies in the system. All right, so let's now move with, we'll do the acceleration analysis. Okay, so for the acceleration analysis, we're going to work it just as the same way that we did for the velocity analysis. We'll start where we know some information. In this particular example, it's at that crank AB, and we'll propagate that information to additional links in our linkage by understanding that the acceleration of points that are linked up together will be the same regardless of which link you're particularly looking at. Okay, so start at link AB. And here we will write that the acceleration of B, this is our general relative acceleration equation, is going to be the acceleration of A plus the angular acceleration of AB crossed with the position vector locating B from A, plus our angular velocity AB crossed with angular velocity AB crossed with the position vector locating B from A. All right. A couple of things we can sort of identify straight away is that since point A in this particular object is fixed at this particular location, that the acceleration will be 0. All right, so I'll point that out straight away because this is fixed. All right, so useful, helpful. Next thing, let's define some of the other bits of this equation. We'll say that omega AB, we know from previous, negative 209 k hat radians per second. We also know the position vector of B from A. You can use trigonometry to get this. We know that this length from A to B is 3 inches, and the angle with the horizontal is 40 degrees. So just with some trigonometry, I'm going to cut to the chase here and recall that this is 2.3 I hat plus 1.93 J hat. And units here are inches. All right. So with this now, we're sort of ready to do the analysis here, except we have to understand one more thing, and that is what is the angular acceleration of this link AB? Okay, so one last thing we'll note here is since omega AB is constant at 209 radians per second, that was given in the problem, angular acceleration I'll give you a second to go ahead and pause the video if you want to think about this. Just kidding, this is live, unless you're watching this on YouTube, in which case, come to the live lectures. Okay. The angular acceleration, if your angular velocity of constant, obviously will be 0. So if we want to make this perfectly clear, we can say the angular acceleration of link AB is 0, or if you want to put 0 bar over the top, 0 vector, because we're supposed to have vectors and that's the way the world works, then that's what you can write. Okay, the angular acceleration of this guy is the 0 vector because the angular velocity is constant. All right, so now we're ready to punch numbers into our equation here and say that the acceleration of B, now here with numbers, is going to be 0, which is the angular acceleration, or generally the acceleration of A, plus here we have 0 crossed with the position vector locating B from A, which obviously will be 0, plus here now we have some portion of the centripetal acceleration, which will be omega cross R, which will be something like negative 209 k hat radians per second crossed with negative 209 k hat radians per second crossed with the position vector locating B from A, which is 2.3 I hat plus 1.93 j hat inches. All right. Just a reminder, there is an additional set of parentheses here. So we got to make sure that we get those included. You want to do the sort of second portion of this first, the K cross R. The omega cross R needs to be executed first, because if you did something like K cross K, you would get 0, and that would be bad sorts of things. Okay, so make sure you're executing the back end of this particular equation first. All right, so this is our general setup. Everything on the right-hand side here is known, so we can just go ahead and solve for this directly, and you'll get here that the acceleration of B after executing your cross products correctly, hopefully, will be negative 100,500 I hat minus, my pen ran out of ink again, minus 84,300 j hat, and this will be inches per second squared. Okay, remember acceleration, length per time squared. All right, so that's your acceleration of point B. All right, pretty straightforward. And now we take this and continue on with our analysis by continuing on to link BD. And again, we're going to write an equation that will be burned into your memory that you're going to see over and over and over. And that is, here we're just sort of changing the subscripts. The acceleration of D is the acceleration of B plus the angular acceleration of BD crossed with position vector locating D from B plus the angular velocity of BD crossed with the angular velocity of BD crossed with the position vector locating D from B. All right, so again, just using this relative acceleration equation. And this we know from previous, from above. Not like in a holy sense, we know from above. It's known from above on this writing pad. Okay. Some of the other things that we know, the angular acceleration, the angular velocity, BD, is known from previous. We solved for this during the velocity analysis last week. We know this to be 61.9. j hat radians per second, and that's from the velocity analysis. All right. We know the position vector of d from b, and this is using trigonometry. We did it with law of sines before, so I'm going to write this directly. If you can recall that this was 7.76 I hat minus 1.94 j hat. This is inches, also from velocity analysis. All right, so we're making our way. One other thing we'll notice is that the acceleration of d is going to be contained to the I direction. So here we'll say it's the magnitude of the acceleration of d contained in I hat. So again, it's contained in sort of this x-axis or horizontal plane. So we know it's going to be contained into the I direction. And we can also say that the angular acceleration will be contained to the z-axis or k hat. And we'll say that the angular acceleration of our particular link, so alpha bd, is whatever the magnitude is contained in k hat, right? So useful. So I think we've kind of defined as much as we can define for this particular problem. So let's go ahead and solve our equation. So we're going to write something like the magnitude of our acceleration vector d in I hat is equal to the acceleration of point B, which we know from before. So this will be negative 100,500 I hat minus 84,300 j hat. This is inches per second squared. All right. We're adding to this. What is the tangential component of our fixed axis acceleration? So this here will be plus alpha bd k hat crossed with our position vector, which is 7.76 I hat plus, minus 1.94 j hat inches, plus what is the final centripetal term, which is omega cross r, which with numbers will be for us, remember our angular velocity 61.9 radians per second. So here we have 61.9 k hat radians per second crossed with 61.9 k hat radians per second crossed with our position vector locating d from b, which is 7.76 I hat minus 1.94 j hat. All right, so a lot to this. Remember this first guy, this is the translational acceleration of d that we know from b. This guy here is the tangential acceleration, which comes from the relative fixed axis rotation of b with respect to d. Sorry, d with respect to b. And this last component here is coming from the centripetal portion, or sort of this normal acceleration that results from the fixed axis rotation of d about b. Okay, so these are sort of our three acceleration terms that sort of pop in to this particular expression. Okay, so a lot going on here, but in fact, we only have two unknowns in this equation, and we have two equations. Remember, this is one equation in I, one equation in j, and we have two unknowns. That is the acceleration of d, the magnitude of that acceleration. And here we have the angular acceleration of rod BD. Those are our two unknowns. All right. Wow. It just went all the way back to the beginning there now, didn't it? All right. So let's kind of bang this out, and we'll look at the two different directions. Let's start in J. Since J is not represented on the left-hand side, so we can write here 0. And you can sort of work your way through this, but negative 84,000 300, which comes from sort of the translational component. And then the two terms that are going to pop up from the tangential and centripetal portions are going to be here plus 7.76 alpha BD. And then here we have a plus after doing this last portion of the cross product, 7430. This will be inches per second squared on this general equation. So we can solve this for our alpha BD. And you'll have that alpha BD is going to be equal to 9,910 radians per second. Second squared, sorry. Just what you were all thinking, right? You all did that in your head? I did it in my head. Just kidding, I didn't. I have it written down. So in vector form, 9,910 k hat radians per second squared. All right, so this is one of our answers. Remember, we have to present it in vector form because it is a vector. And also, let's look at the other portion of our equation. We also have the I hat portion of our equation. And that here will be, we have the magnitude of alpha D sort of on the left-hand side equal to, here, negative 100,500 coming from the translational component, plus 1.92 times alpha BD, which we now have is 9,910 radians per second squared. It's our angular acceleration. So this is the tangential component of the acceleration coming through here. And then the last little bit, which comes from the centripetal portion, is going to be minus 29,700. And again, units on this are inches per second squared. All right, so after this rigmarole, you get that the magnitude of the acceleration of D is going to be equal to negative 111,200 inches per second squared. Or if you want to write the acceleration vector properly, we have that the acceleration of D is negative 111,200 I hat inches per second squared. Some big numbers there, but that's the general idea. Okay, hopefully we stayed awake. If not, run it back on YouTube, I guess. That'll be it for today. I'll stop the recording. I'll hang out for a couple minutes if people have questions. Otherwise, thank you for